Let's talk about separation of variables. We'll continue on this. We got partway through the process last time, so we're going to finish up the process today and hopefully show you what it looks like in an example. So remember where we left off, right? We started with this 2D problem. It's actually a 2D problem. We had these boundary conditions that we decided were homogeneous in one direction. We said t at x equals 0 is 0. And so this is a homogeneous boundary condition because it's 0. It's not a realistic temperature, but maybe we're modeling this with reference to some other temperature. And then the boundary condition on the right-hand side was dt dx equals 0. So we said this x direction is homogeneous, and that allows us to solve this problem using separation of variables. And then we wrote here, this is our mathematical statement, right? This is our mathematical statement of this problem. We have our governing partial differential equation in two dimensions, and then a statement of all the boundary conditions. Okay, so this is the problem we're trying to do. All right, and how far did we get last time? Let's see. This is, looks like my notes didn't fully update. Oh well, we'll go through it this way. Okay, so how far did we get last time? Well, we got as far as step 3 here. All right. So in step 1, we went through and we checked that our problem met the requirements for separation of variables. That was the first thing we had to do. We talked about the boundary conditions. Everything's linear. Like there's all those criteria we had to go through. We decided that was the case. Step 2, then we went and tried to separate the variables. So we're coming up with an equation for temperature as a function of x, an equation for temperature as a function of y. And then those two things will multiply together to give our full temperature solution. Okay. So first we went through and separated the variables and found this is our equation for x, and this is what we ended up solving. And we decided that it was really important to figure out what's the sign on this lambda squared. And the sign on the lambda squared has to be chosen carefully based on which direction is our homogeneous direction. So we want the homogeneous direction to have this ODE, where it's a plus lambda squared times whatever. And then we want the non-homogeneous direction to have the negative. Right? It wasn't entirely clear why that was, but we'll see today how it all kind of comes back together. All right, step 3, then we solve the Eigen problem. An Eigen problem is a problem in which there are essentially a bunch of solutions and you add them all together, right? So the Eigen problem that we had was, okay, we came up with this solution for t of x. So this equation satisfies this ODE up here. C1 sine of lambda x plus C2 cosine of lambda x. So this is the solution here. And then we had to enforce our 2 boundary conditions in x, in the homogeneous direction. Right? If y was our homogeneous direction, we'd be doing this for y first. So we first enforced what? We enforced t at x equals 0 equals 0. We got what? Yeah, we were able to cancel out C2, right? This part. And then we enforced this boundary condition and we got to this statement here. This is our Eigen condition. Right? This is the thing that we have to satisfy in order to figure out what our values of lambda are going to be. Okay, so based on our Eigen condition, we come back and we say, okay, well, this Eigen condition is satisfied in every single instance where lambda is a certain value, right? If there's this repeating series, every time lambda is a certain value, cosine of that function is going to equal 0. So we came up with this expression here that just says, all right, well, this is 0 every time we have pi over 2, 3 pi over 2, 5 pi over 2. That's given to us by this expression based on the index I. All right, so we now essentially have an infinite number of solutions here, an infinite number of lambda values that we can use to generate a temperature solution. So now we say for an ith temperature solution, we have an unknown constant C1I, and then we have our Eigen function. Right, our Eigen function is the original thing that kind of came from the boundary conditions being enforced up here. So this is as far as we got. And hopefully looking at it a second time, you can kind of see how we got to this point. But the critical thing is we have a bunch of solutions one for each lambda I, where lambda is the point that gives you that intersection for the Eigen condition at 0. And then we have, now we have to enforce those lambdas in our original equation, and we have Tx at I now with this unknown constant at each position. Okay, so where we're going to go today now, we're going to do steps 4 and 5, and actually there's 2 more after this, but my notes for whatever reason didn't update. So we'll get to these. We're going to solve the non-homogeneous side and start putting things back together. Okay, so let's see here. All right, so I've just copied here what we had in terms of our X solution, right? We have the X equation. What we need to do now is we've identified the fact that lambdas there's a bunch of lambdas. So our original ODE says, right up here, it says this is for X. So now for lambda in this equation, that lambda carries through the entire problem, right? And now we need to enforce this also for the Y part of the problem. So in this step, we're going to start solving the Y part, the non-homogeneous part. Okay, so let's do that. So let's write out our Y condition. It was d squared ty dy squared minus lambda squared ty is equal to 0. That's our Y ODE. Now we have to write this in terms of the lambdas that we've identified before, right? We now don't have just one lambda, we've got a bunch of lambdas. So this just becomes d squared ty dy squared minus lambda I squared ty I, right? So now that actually there's an I on both of the ty instances there. So we're finding a solution for a particular lambda I. Okay, and this is equal to 0. It's equal to 0. Okay. Well, what's the solution to this equation? You could go look in a table in the textbook. You could plug this into Maple, and you would find out that, all right, ty, the solution for this equation for an ith one is some constant c3. Now it's an ith constant, so c3i times cosh, hyperbolic cosine of lambda I times y, plus c4 I times sinh of lambda I times y. Okay, let me see what this is. Yeah, so, okay, so then we now have our y solution, right? We have a y solution for every value of lambda, but this we don't know what these constants are. Right? This is kind of the problem. Let's see. Step 5 is we're going to determine the temperature solution. Determine the temperature solution for each eigenvalue. So what does that mean here? The temperature solution is Txy. This is our original solution. Txy is Tx is a function of x times Ty is a function of y, right? Now, because we've said, okay, lambda has a bunch of values, each lambda corresponds with a unique temperature solution. What we're actually saying is this becomes Ti at x and y is equal to Txi, which is a function of x, and Tyi, which is a function of y. Right, we're just saying now there's individual temperature solutions for each lambda value. Okay. So if this is true, we've already solved up here. So we've solved up here for Tx. We just solved here for Ty at the ith lambda value. So we can just put them together, right? And we end up with Ti is equal to C1I. That's C1I times sine of lambda I times x. Okay, times what is our Ty expression? It's just what we had up there. It's C3, back up from C3, I cosh of lambda I times y plus C4 I sinh of lambda I times y. Okay. And like, look at what we have. We have now Tx on the left-hand side. We have Ty here, and it's for the ith temperature or lambda term. Right? And so truly, we have a solution that is some function of x. We multiply by some function of y, put them together, and we get a solution for temperature. Okay. Any questions on this so far? Okay. Okay, so then step 6, we're going to assemble all the solutions back together. So here's what we just decided. We said, here's our solution that we just wrote out. One thing that we can do, though, is, I'm just going to look back a little bit here. We can take this unknown constant, C1i, is multiplying, I can multiply through by these unknown constants in here. Right? So what's an unknown constant times an unknown constant? Well, it's just an unknown constant. So we're going to bring that C1i, kind of lump that in with the other unknown constants. And so then we just have 2 sets of unknown constants that are within the y solution. So rewriting that, right, you can see that the unknown constant in front of the entire expression went away here. And we're just left with C3i and C4i for all those lambda I values. So our job is to put this together. So how do we put this together? Right, we now have a solution for I, Ti, but we really want a solution for T, not just Ti. And if you kind of like picture what's actually happening here, I've got expressions here for a bunch of little temperature equations that have some little, features with them, some local features associated with them. I'm saying I can take all those temperature expressions that I have, infinitely many of them, add them together, and that gives me my one temperature solution that I really want. Okay, so how do we combine everything? Well, it's actually really simple. We just say we're going to sum up every single Ti. Right, for, I guess we could say this is for I is 1 to infinity. Right, we're combining all of our temperature solutions in this way. Okay, so if we do that, we're just saying that T is equal to, let me just write it out, T is equal to the sum for I equals 1 to infinity of this whole thing up here. It's sine of lambda I x times C3 I cosh of lambda I y plus C4 sinh of lambda I y. Okay. Some things to point out. Right now, this is our solution. We're not done yet, though. We have these unknown constants. So how do we get to this point so far? We've taken our solution for x. We enforced boundary conditions. We enforced these 2 boundary conditions in x. That the enforcement of those boundary conditions is what gave us our eigen problem and let us solve for the eigen condition. Right? That's from the homogeneous boundary, the boundary conditions in the x direction. That's how we got to that point. We have not done anything yet with y. Right? Y has not yet been forced to match this problem, or the problem hasn't yet been matched to force the boundary conditions in y. So that's our next job. We have to now employ the y boundary conditions to solve for these remaining unknown constants. If you're looking at this and wondering how we're going to do that, right? We have essentially infinitely many unknown constants times 2. And we have 2 boundary conditions. Right? How is that going to work? Well, we'll see. Okay.